Let's see. What's happening? What are we doing today? That's right. Ready for... Oh! Look at that! Look at that! Tropical Geek. Wow. Amazing. Best student ever. Okay. Hello, hello, hello. Oh, where's the music? Spotify. Awkward. Okay, class. Hope you're here. What am I doing today? We're gonna finish up this proof that A5 is the only simple group of size 60. So it is the first interesting element in the periodic table of finite simple groups? Me? Oh, really? That's that better? Okay, good. Awesome. Okay, so let me start now. I have 45 minutes. Where did we leave off? Let's kind of reorient ourselves as far as where we left off last time. So we know we have a group of size 60 and it's simple. Pretend. Then what does Silo theory tell us? It tells us that okay, so let me say something. This is an observation. If at any moment we exhibit a non-trivial homomorphism to S5, we're done. Why? Because that homomorphism has to be injective. Because kernels are the normal subgroups in this world. Okay, so it has to be injective. So it's an isomorphism onto its image. But its image is a group of index 2, size 60 in S5. Because so A5 is the only group of index 2 in S5. That was an exercise, or you just use index math. I think I called it index math. Just use a little bit of index math. A5 is the only subgroup of index 2 in S5. Okay. I'm also subtly using I'm also in that index math, I'm using simplicity of A5. Okay, so there it is. G is isomorphic to A5. If at any moment in the tree of logic you exhibit a non-trivial homomorphism to S5, you are done. So that's always remember this running observation. Okay, so what we had deduced, when you're doing Silo theory, just factor the size of the group. Okay, so what we saw last time is that the number of Silo 5 subgroups was exactly 6, I think. 6. The number of Silo 5 subgroups have order 5, by the way, so they're cyclic. Wait, what happened to my red pen? They're cyclic, all right? So these are all cyclic. Silo 3 subgroups. Oh, wow. And Burroughs totally comes in and showers us with just wealth. Just spills all their wealth into the chat. Amazing. Totally overkill and completely unnecessary. and now places a burden on me. So expect 500 wealths in your chat. No, much love, N. Burrows. Okay, everyone go check out N. Oh, shout out N. Burrows. N. Burrows chemistry teaches chemistry on Twitch. One of those. You know, there's like 2 of them. N. Burrows, 3 of them. Melko and Gath. The symmetric group acts transitively on that set of 3, so I won't. There's no order. There's no like definite order who's top bottom, but S3 sort of acts transitively, so you know, I won't do that. Okay. I don't. It's saying to press thank you 10 times. Enter, thank you. Okay, shout out. N. Burrows. Okay, awesome. Go check out N. Burrows, everyone. All 3 of you. Okay, so Silo 3 subgroups. How many Silo 3 subgroups are there? I think we had deduced. Well, let me just go through it again. There can't be 4, because then you'd get a non-trivial homomorphism to S4. Bad news. There can't, so there has to be 10, I think. 10. 10 was the thing. I'm just going off of memory. I don't use notes. I don't have a secret extra note thing, which is probably a disaster. Okay, then the number of Silo 2 subgroups, which have size 4, by the way. Right? But we call them Silo 2 subgroups, class. Just the language. This, we had to like debate. There was a debate. So here, this is where we left off. So what we have to, the work we have to do, the work ahead of us, is to establish that there are not 15 of these. That's the only case. 15 comes out of Silo theory. That's the power. You don't have to check all tons of possibilities. You just have to check a couple. All right, and each one is going to have some ad hoc special argument, because all the little groups are their own little gems in this world. All right, good. So let's go and try to do this. All right. Okay. So, 15 of these. How many elements? Let's think about this. How many elements? There are 15 elements left. By left, I mean unaccounted for. These are, you know, this comprises 45 elements in here. And so there's 15 left. Okay. Yeah, no. Silo 2 had 2 possibilities. There was 2 possibilities. There were either there was 5, in which case we're in the golden observation. Let's call this the golden observation. All right? So once you get a 5, this is gold. All right? And what I'm saying is we need to now establish why you can't have 15. Or, you know, it's like a logic tree. Okay, let's suppose there are 15 now. If you can still get to G acting on a 5-element set, you're still good. Okay, so that's the nature of the argument. All right, so how many elements are left? 15 elements are left. Okay, so let's pick a Let's pick a Silo 2 subgroup. Let's call it A. Here's A with this little identity element and then 3 non-trivial elements in it. All right, this little picture of A. Little, I know there's some scientists, it's little mitochondria, okay? Now, I'm now gonna consider, now, how many Silo 2 subgroups are there? There are 15. But notice that they have order 4, so they can overlap all complicated and stuff. Kind of sucks. Like, combinatorial mess can emerge when you're trying to see how they can overlap and so on. Okay, so what I'm gonna do is try to gain clarity on that. So let's think about this. Let's pick an element, little a. Okay, question. Okay, let's go slowly. Question. How big is the conjugacy class of A? Under the conjugation by all of G. Okay. It has to be, the conjugacy class has to be a subset of these 15 elements. These 15 elements, conjugation mixes them around. Permutes these. Why? Because conjugation clearly leaves all of the Silo 5 subgroups, mixes them around, mixes all the Silo 3 subgroups around. So if you look at the complement, it stays stable under conjugation. Okay, so I took an element little a, took its conjugacy class. That is in this set of 15. Okay, how big is the conjugacy class of A? The answer is the size of the group divided by what we call the centralizer of an element. It's the set of elements in the group such that G times A is A times G. The things that commute with A, or if you want to write another way, that looks more like centralizer. That looks more like a stabilizer under an action, right? Okay. So this is the Z of A is the stabilizer of the element A under conjugation action. Okay, so orbit stabilizer tells you that this is the size of the class of the conjugacy class. Okay, so what do we know though? What do we know? We know that A, this group, is a group of order 4. So it's abelian. And so A has to be contained in the centralizer of little a. Little a commutes with everything in A because little a is in A. That's a commutative group already. Good. Can the centralizer be bigger? Let's think about that. Um, what are the possible sizes of a bigger subgroup? Well, then the size of the centralizer is a number dividing 60 and divisible by 4. The size of A. So if you think about that, there aren't that many possibilities. In fact, so if you think about that, you get is either you get this class conjugacy class size is either 5 or 3. Okay? Now we know can't be 3. Because then you'd get a non-trivial homomorphism which is bad. You'll get a kernel, non-trivial kernel. All right? If it's 5, you're still done. This is gold. So we can assume that the conjugacy class of this element has size 15. i.e., A is the centralizer of the element. Okay, so we get to assume that. Because in other cases, we're done. It's a big, massive case check. In the other cases, we still exhibited an isomorphism with A5. Awesome. So let's assume that. Plus, we know that there are 15 Silo 2 subgroups. All right, so we know these two things. And capital A was one of them. But hold on. Look at this carefully. This means that the 15 remaining elements are all conjugate to one another. Okay, so any group theoretic fact about one of them is holds for all of them. This is like a vague statement, but I'm going to use it. Just watch. Okay, let's see what I mean. Okay, now I'm going to actually try to investigate the way the petals of the two Silo subgroups kind of overlap. Okay, so it's a complicated picture. Flower. We have 15 petals. And let's say one of them was our group A that, we just highlighted one of them. There's A. Okay. We know that the petals can't all be like disjoint from each other. Like maximally disjoint, because that would be too many elements. That would be 3 times 15, which is 45 distinct elements. We have 15 elements to play with. Remember, we have 15 total elements. All right? So there's got to be a lot of overlapping happening. So let's ask the following question. Given an element in the set of 15 remaining, how many Silo 2 subgroups contain it? All right, we have 15 elements remaining. they form one, we're assuming they form one conjugacy class. That's our assumption. They form one conjugacy class. I'm asking a question about one of the elements. How many Silo 2 subgroups contain it? Okay, here's the key observation. The answer does not depend on the element, because all elements are conjugate. If you have an element A and a Silo 2 subgroup containing it, if you take another element A prime and some Silo 2, then A is related to A prime by conjugation by some element. But then just conjugate that capital A subgroup to get a subgroup, a Silo 2 subgroup containing this one. But this sets up a bijection between the Silo 2 subgroups containing this element and the Silo 2 subgroups containing that one. Just conjugate to go back and forth. Conjugation sets up a bijection between the set of Silo 2 subgroups containing one element and the set of Silo 2 subgroups containing the other. So the answer, the number here, is independent of the element. That's great. So let's take a look at what this says. Given an element, how many Silo 2 subgroups contain it? All right, the answer is independent of the element. And here's the great thing. That this centralizer has exactly 4 elements. So the centralizer that means that there can be only one there can only be one Silo 2 subgroup containing this element A. Why? Look, you have an element. It's really easy. You have an element, and suppose we have a Silo 2 subgroup containing it. And then suppose there's another Silo 2 subgroup containing it. All right? They're both order 4 subgroups, so if they intersect, they can only intersect at a order 2 subgroup, and that order 2 subgroup has to be identity plus A. All right, so I've drawn this. Okay, imagine there's 2 Silo subgroups containing the element little a. Each Silo 2 subgroup is an abelian group because it has order 4. This is an abelian group. And this is abelian. And so in this picture, I can see 1, 2, 3, 4, 5, at least 6 things that commute with A. But that's contrary to our assumption. Our assumption was, suppose the centralizer was 4, meaning the orbit of A under conjugation was 15. All right? So this contradicts our assumption. So what's the conclusion? We conclude that the Silo 2 subgroups would have to be least overlap. Pairwise intersect at only the identity. In other words, we get into that picture the flower theory picture with 15 petals. 15 petals. Each petal has three non-identity elements. And so that means there's 15 times 3 unaccounted for elements. Which is absurd. Because there's only 15. All right? So we conclude that the centralizer of this element can't only be 4. This can't hold. Okay, that was an assumption. Look, assume that the class, conjugacy class, has 15 elements. In other words, this was true. Can't be true, because the flower's petals would all be disjoint, so to speak. That means we're in this situation. We're not in the 3, so we're in the 5. And we've exhibited a homomorphism to S5 even in any case. Awesome. So in every case, in any conclusion is all paths lead to a homomorphism. A non-trivial homomorphism. Which has to be an isomorphism. Okay? Actually, if you trace through the case, all the case checking, actually what you notice is there must only be 5 Silo 2 subgroups. And this homomorphism phi can be the homomorphism expressing conjugation action. On the set. All right. So I actually want to emphasize a general theme at this point. The general theme. Okay, so there's a big, huge pattern in group theory. Okay, so what we just saw was a theorem in group theory. Any simple group of size 60 has to be isomorphic to a very particular group, A5. Okay, in the beginning, before you learn all the levers and the tricks and the Silo theorems and so on, such a theorem looks impossible to prove. It's just imagine the days of group tables, folks, students. It seems impossible. However, whenever you're in this situation where it's like, wow, what a remarkable conclusion. There's only one, and it's A5, very specific. The general theme is as follows. It's very vague, but it's a massive motif, okay? So the general theme in group theory is investigate how a group G acts on pieces / like organs of itself. You see, if all you have is a vague group G and all you have little information, 60 elements, how are you gonna get to a specific group like A5? The general theme is make the group act on things that are simply grown within itself. You know, look at the internal anatomy of the group and find actions of the group on the various objects inside of itself. That's the only way forward, really, folks, because all you have is the group, G. It's just a vague set of letters. How are you going to get to a concrete situation? The answer is look within. Look at the stuff intrinsic to the group and investigate how the group shuffles internal organs and pieces around. That's what happened in this argument for why there's only one group of size 60. The punchline is you look at how the group conjugates the set of Sylo 2 subgroups. That is what I mean by intrinsic anatomy. The set of Sylo 2 subgroups form these like organs in the group, and the group permutes them by conjugation. This is like huge. You read all the textbooks forever. Become a group theorist, you'll see this universal theme. How do they get such amazing conclusions? From a general situation to a specific group. It's always, 100% always, the group ends up acting on something intrinsic to itself. Remember that. Okay, so now, just for fun, I'm going to show you a group of size 168. Okay, I'll just tell you right now, this will be the second entry in the periodic table of simple finite groups. Okay, why simple? It's like atomic. It doesn't admit any kind of intermediate quotient. It's not built out of like a quotient with a little kernel. It doesn't crumble like that. Second group has size 168. That's why I asked you to stop in this massive homework assignment / exam at 168, because there is an interesting group there that doesn't have any quotients, non-trivial quotients. So let's look at this group, or non-trivial normal subgroups, distinguished subgroups. Interesting anatomy that you can hold on to. Okay, let's look at this group. I'm just going to show it to you because it introduces an idea that transitions us to the next phase of the class, which will be ring theory and field theory. That's why I want to show you this group. Okay, so first what I'm going to talk about is just really briefly, I'm going to talk about bizarre math. Okay, let's talk about a bizarre math world. Okay, it's going to be called F2. F2 is a number system, it's a field, that has only two elements. You know it right now as Z mod 2Z. You know it? It's the same. But right now we've only been focusing on the addition structure on Z mod 2Z, thinking of it as an abelian group. But you might have learned in 3613 that you could also multiply two remainders in Z mod NZ in general. That extra multiplication structure is part of the next phase of the class. It forms a ring. You get adding and multiplying, two operations to juggle. And F2 is the name of the ring that we're thinking of. When we try to emphasize, we're also thinking about multiplication. So what is it? You've got two numbers called 0 and 1. And you know how to add them. 0 plus 1 is 1, 0 plus 0 is 0, etc. 1 plus 1 is 0. Okay? That's how you add in F2, in Z mod 2Z. How do you multiply? Okay, multiply. I'm just going to tell you how to multiply. 0 times 1 is 0. 1 times 1 is 1. And that's it. All right, that's how you add and that's how you multiply in this bizarre number system. Okay, that's how you do it. there's only zeros and ones to talk about. Odd and even. That's how, it's the mathematics of even and odd numbers. That's all we're doing. 0 means even, and 1 means odd. And you get like odd plus an odd is an even number. You all know this. Okay, so out of this field, out of this number system, I'm gonna produce a group. Here's a group. It's called GL3F2. This group is called GL3, like GLN, but of F2. And what is it? It's the set of 3 by 3 matrices with entries in that number system. Okay? Look, I'll show you an element, but not all of them. Not all of them. Such that the determinant, which you compute just by like same method, you know, expansion along a row, whatever method you have, such that the determinant is not 0. 0 meaning 0 in this bizarre number system. Okay? Let me show you an example. For example, this element. Oh, and the group law is matrix multiplication. So for example, this thing is literally the identity element in this group. All right, this one. Here's another element. If you compute the determinant of this thing, you'll get probably -1. But you know, -1 is 1. You can see 1 equals -1. So, you know, -1, math is really easy here. Okay, good. Determinant is non-zero. Good. There's all kinds. You can do this one. This is another element. Now, you might have a question. How do you count the number of elements? Okay, if you haven't seen this before, this can be a tricky math problem. This can be tricky. It can be tricky. Okay, but the best way to go about it is to kind of think about linear algebra. So think about dependency of vectors. Like, when is one vector linearly independent from a second vector? And you go kind of column by column when constructing the matrix. So that's the little hint that helps you find the size of this this group. All right, so this is tricky. What you do is you think about constructing column by column. Construct a set of linearly independent columns. Now it's a little bizarre because you're in bizarro math. So linear independence, what constants are you allowed to multiply by? Only these numbers. So these are like the constants. in your linear algebra. You're only allowed to multiply by zeros and ones, which makes life really easy. So like, for instance, the first column can be anything. Except it can't be what? It can't be 0, 0, 0. Can't be 0, 0, 0. So that's like so on and so forth. All right. So then you have to think about what's the possibilities for the second column and then the third column. And what you get is a total of 168 elements. If I did this right. Wait, what's the question? Yeah. Okay, this is a troll. Okay. So this is a group of size. Wait. But hold on. Am I doing this right? Hold on. Let me just double check this. Did I just lie to you? Wait, did I do this right? Hold on. Am I just being an idiot? Hold on. Let's do it carefully. Yes, I did it right. Okay. So, yeah. This is harder than I anticipated. So once you choose the first vector, for example, then you have to ask, how many choices do I have for the second column of the matrix? Now I remember. So how many choices for the second column? Once you choose this as first column. Well, you have to make sure that you don't choose a multiple of the same vector. But here, non-zero just means 1. So you just don't choose the same vector. So you choose, what is that? So that means, how many total vectors are there? You get 2 cubed minus 2. Yeah, 2 cubed minus 2. There's the 0 vector. Don't choose that. And don't choose this one. So 2 cubed minus 2 choices. So we had this many 2 cubed minus 1 choices, then 2 cubed minus 2 choices for the next column. Okay, now how many choices for the third column? Okay, let's say you chose 1, 0, 1, and then 0, 0, 1, for example. What can you choose for the third column? Well, you can choose any number, any element which isn't like a sum of these two. or one of them, or the other one, or 0. So you can't choose any linear combination of the first two. Right? The first two. But how many linear combinations are there? This is simple. The coefficients are either 0 or 1. So either take 0 times the first plus 1 times the first plus 0 times the second, 1 times the first plus 1 times the second, etc. So can't choose any linear combination. There's exactly 4 of these. 0, 0, 1 times the first plus etc. 4 of these, or the last column. So the last column has 2 cubed minus 4 possibilities. So in order to create an invertible matrix, determinant 1 matrix over the finite field with 2 elements, you have a total of this beautiful expression. This many of these kinds of matrices that have determinant 1. Now, if you multiply this all together, you get 168. Okay? So what's the point? This is a crazy weird group, right? I showed you one crazy place where it shows up. This group is the second entry in the periodic table of finite simple groups. All right, and the question, finite simple group of is non-cyclic. Then now there's a mega problem. How does one prove such a thing? How do you prove this? That's a true statement in this. There's only one finite simple group of this order. And the question is, how the hell do you prove something like that? Because now we're just in A5 is at least a permutation group of some sort. But now we have a crazy group of matrices over a weird finite number system. F2, odd and even mathematics. Matrices with 0s and 1s in them. Binary matrices. That's crazy. How on earth do you get any kind of communication from a general just G that has 168 elements to this? What are we gonna do? It's way harder. It's trickier than the case of 60. And so in office hours, I'll play around with this group. I'll show you other places where the group shows up in other parts of other manifestations of the same group. All right, so that's what I'll do. In office hours, I'll play around with this group. We'll apply Sylow theory and see what we can say about such a group in general. A finite group of order 168, which is simple. And probably we won't get to prove the exact statement, but we'll start to see that there's a chance, at least. There's some hope of proving this much more difficult version of the 60 theorem that I proved earlier in class. That's what I plan on doing in office hours at 5. Okay. All right. So yeah, we'll find the same group, but with different. Yeah, we'll find another way of talking about this particular group, but they're all secretly isomorphic to each other, obviously. But it'll be fun. I'm just looking at chat. Okay, good. We still had to come to class because he was teaching. Yeah, that sucks. Okay. Oh, I also probably should share an announcement. So, shungite? Yeah, Tropical needs shungite after that traumatic experience. But the Thilo theorems are very powerful. They get you to a finite list of cases or situations to analyze, students. And analyzing this individual situations will definitely be different group by group. And you do have to sort of hope for some nice stars to align. But the combination of like narrowing down to a finite number of cases plus counting arguments. Flower theory is just counting argument, if you think about it. I mean, that's what we're doing. Counting argument. Those can get you really far. And Lagrange's theorem, divisibility of subgroups, orders inside of larger group. This can get you very far in life. That's what we're witnessing. And so review the case checking in the theorem that any group of order 60 is any simple group of order 60 is A5. Isomorphic to A5. That's it's awesome that we can even do such a thing, if you think about it. Okay. Yeah, announcement. We're someone in the chat named Algebraically Challenged. You might see him every now and then. We're gonna try to record some more advanced topic stuff videos. It's in the subject of algebraic geometry, but like elementary, like for people learning. It's intended for people who want to learn and want to see more concrete examples of the objects of algebraic geometry. We're gonna do some recording sessions on Thursdays. But what I want to tell the people who are not used to it, I will be wearing a wig on Thursdays. So I might look different than my usual look. Like this is me without a wig. I will be wearing like a disguise on Thursdays, and I might be a little bit more serious and different on Thursdays. So, maybe don't come. It's just me and Algebraically Challenged hanging out and trying to create some videos, recording some videos in algebraic geometry. So that'll start happening next week, hopefully. So I will be wearing a wig on Thursdays, folks. That's why I will look different. I just want to warn you, if you see me on Thursdays and I look totally different, that is me wearing a disguise. Okay? Awesome. That's all I wanted to warn you about on Thursdays. Can you give us an early look of the wig? No. You'll see it on Thursday, Crow. You'll see it on Thursday. This will be on this channel, Kappa. Here, we have a serious task. Me and Algebraically Challenged are working on a project. It's a serious project. The project where I'm developing videos for future use when I teach algebraic geometry again. Trying to make them effective videos on concrete stories in algebraic geometry. So yeah, I'm gonna just do it here and talk to chat. Between takes, I can talk to chat and see what degeneracy is going on, and crucially talk to Algebraically Challenged, and it can be a fun time creating these videos. It'll be at 2:30 Central Time. I think, right? Algebraically Challenged? AC? Oh, I should call you AC. AC, is it? 2:30, yeah. 2:30 Central Time. So that's gonna start on Thursdays. I mean, AC and I will have fun. I don't know how it might be a little strange for others, but you'll get to see what kinds of stuff AC and I think about. Which I know some of you wanted to see more of, but first row? Tropical Geek, you're in the first row of like every science and tech channel though. So I don't know how much. Yeah, I don't know. When you say you're gonna be in the first row, okay. Like you're in the first row of everyone. Like, can you commit that you will close all the other tabs? Then I'll feel like, wow, there's some loyalty there. You can commit to that? Okay. Yeah, you probably have like every science and tech streamer up right now, right? I mean, seems like it. Yeah, you see calc math in a programming channel. Yeah. These traders, man. They're just traders. You can't trust them. Unfaithful. Exactly, Kappa. You too, Kappa. Yeah. No loyalty these days, seriously. I don't know about you, Davis. I haven't been stalking you, but Kappa. Yeah, the only person I don't see in any other channel is the fake wife. Kappa, I agree with you. I think that's the only person that's, loyal. Oddly. Okay, so class? Not class, but friends. I mean, these are just friends now. I have to go learn some Calc 2. Kind of divergence test. Okay, great, Tropical, great. So let me roll the credits. Hello. A5. GL3, F2. And then right under that, Tropical Geek, for being teacher's pet. I need a designated song for credits, right? That way that people know it's time to wrap up. I don't know what to do. Maybe what's the song from Barney? Do you guys remember Barney? Like the purple dinosaur? I don't know why it just came back to me, just childhood memories. But what that song? Okay, so Tropical Geek. Yeah. Okay. Tropical Geek. Then Crow, of course. Okay. Algebraically challenged. Mod. What are the mods we have? All right. Oh, N Burrows was here. YouTube celebrity. I mean, Twitch celebrity. It's quite an honor. N Burrows too. Oh, also okay, then who else was here? Yeah, BPS not awake. I don't think he's awake. Okay, what else? Kappa. For realizing Vmod 60Z ain't simple. I saw that, Kappa. I saw that. Don't think I didn't see that. All right. Then who else is out there? Oh, Will. Color is the tag. Gray? Wait, is Will's? No, it's orange. Okay. Which is appropriate given school. All right. No one else really. Oh, so this random person. You're cute. And then an interesting. I assume they mean 42,069. I assume they want to put a comma here in this 5-digit number. Interesting choice of number. Not sure. Okay. Awesome. So I'll thank them showing up. All right, folks. I gotta go learn stuff, and then teach it. So. Oh, you're right, Kappa. You're right. Yeah, it's 42. Right. I'm sure this person was referencing 42. Guide to the Galactic Traveler. Guide to the Galactic Traveler. Is that what they call it in wherever you're from? Germany? Are you from? You're in Germany somewhere, right? It just sounds hilarious when you call it Guide to the Galactic Traveler. Okay, I don't know. I thought I don't know. France. France, okay. Guide to the Okay, okay. Okay. Hey, Smash Time. Smash Time is a esteemed mathematician and made it just in time for the credits. Yeah, Smash Time is yeah, he's a mod. These are mods. So Crow? Yeah. Be careful. You're saying that in front of a bunch of mods. I am pro censorship here. The mods at any moment. Boom. You're gone. Yeah, they have that kind of power. Good job. Good Smash Time fools. Ah, yeah. So you have money in front of your name. Exactly. Yeah. So be careful of the mods, don't, stay on their good side. All right. Good to see you, Smash Time. We're just rolling through the credits here. We're gonna credit Silo, A5, GL3F2, and then a bunch of people. I mean, Silo was a person too. I mean, let's be honest. Here we go. You want some music? How does that one song go?